Welcome to University Place Presents. I'm Norman Gilliland. Perched atop a hill overlooking Lake Mendota in Madison is the Washburn Observatory. It has been observing movements in the sky by stars and planets and other entities since the 1880s. And along the way, it has transformed the way we think about the universe. We're going to find out how from my guests, and they are Jim Lattice, the director of the uw-Madison Space Place, and Kelly Terrell, science writer, and they are co-authors of the book Chasing the Stars, published by the Wisconsin Historical Society Press in 2024. Welcome to University Place Presents.
Thank you, Norman.
Yeah, thank you, Norman.
Looking at the observatory itself is a fascinating thing because there it is pretty much now in the middle of a campus, a university campus, although it is prominent as it overlooks the lake still. Why did it get chosen back in the 1870s?
Yeah, it was on the western edge of campus at that point, part of the large expanse that stretched westward that used to be called the University Farm at times. And it was far enough away from the city, but although the city was small at that time, but far enough away from what modest lights there were, but also smoke, sources of smoke and things like that, which did eventually engulf the observatory anyway. But it was pretty much the westernmost structure of the university at the time.
And whose idea was it?
So it was Cadwallader Washburn, who was a former governor and a very successful businessman. And he was a political ally and associate of John Bascom, who was the president of the university. And they had it in mind to transform the university with a research institute there.
John Bascom was the university's sixth president, and he believed in co-education and saw the university as a place where you could bring students together and really sort of stake a claim for the university as a research institution. And at the time, having an observatory was somewhat similar to having a department of computer science today. It was a way to establish a university as a research entity, and he modeled after places like Harvard and Michigan.
Wisconsin always had this thing about Harvard, didn't they? It would be the Harvard of the Midwest.
That's something like that, yeah.
What kind of telescope, though, if we're talking 1880 or so?
Well, so research telescopes of that day were almost invariably what we call refracting telescopes. Instead of having a big mirror the way modern research telescopes have, it would have a lens as big as you could afford, a lens up at the front of that telescope. And Washburn specified that he wanted a telescope that had a lens bigger, well, comparable to or larger than Harvard's. Yeah, that's right. And so, Harvard's telescope, the one that he was comparing to, was they still have it, a 15-inch telescope. That means the lens, the diameter of the lens was 15 inches. That's how astronomers talk about the size of the telescope. So we have one that's 15.6. We often say 15 and a half inches. And that pushed Harvard down one in the rankings and established, so that telescope was the third largest in the United States when it was installed up there at Washburn Observatory.
What were they looking for? What were they looking at?
Well, so astronomy of that era was very different than what we think of astronomers doing today. We often use the term astrophysics today, which helps distinguish between what astronomers do today. And astronomy at that time was carried out with a number of specialized techniques that amounted to measuring the positions of stars in the sky. That was not the only thing astronomers did, but it was the primary work of astronomers. Sometimes they were measuring positions of the sky in the sense of measuring one with respect to another, so that you might say make up a star chart, a star atlas or something. But sometimes they were measuring one star with respect to another of stars that are in systems, gravitational systems of stars, and you measure the positions of one with respect to another to observe their orbits and try to derive information about those star systems.
Do you have a notion of how far they could actually see?
The ability to see into the universe does increase as your telescopes get bigger, but it's just a question of how dim an object you can look at. You can see pretty distant things even with your eye, just with the unaided eye. So what we usually think of is that these telescopes were not specially designed to detect, say, really dim galaxies, the kind of things that we do look for to tell us how the universe has evolved. And so that's why they could get by with much smaller apertures, 15.5 inches, compared to, say, our large telescopes these days have mirrors measured in meters. And so they have penetrating power into space vastly greater. That wasn't the primary goal of these telescopes.
One thing that I think surprises people that the instruments at a place like Washburn was doing too was actually measuring very accurate time. And so you could look at the transits of stars across an instrument like the Meridian telescope that Washburn was equipped with in addition to the refractor that we've discussed. And by getting very accurate celestial time, observatories could then sell that to industries like the railroad and watchmakers who were very interested in establishing very specific and very accurate timing.
I think, so what would that instrument have looked like?
That's a meridian circle telescope there, and the second director of Washburn Observatory, Edward Holden. A meridian telescope like that was designed to measure the positions of stars very accurately with respect to the horizon and the zenith. And so when a star passed through the field of that telescope, it was on the local meridian. And an observation like that, an astronomer can turn that into a very exact time. So basically they would find the time with an instrument like that meridian circle, and then set the observatory clock from that observation with that telescope. And then the observatory clock was the master clock that was used ultimately to provide time signals by telegraph lines.
All this done by hand? How would they have done these charts?
The observing was done literally looking through the telescope, eyeball at the eyepiece astronomy, and noting, pressing a button really, when the observer saw the star move through there. And that fundamental measurement could be used for actually a lot of different purposes in addition to just the very practical one of finding accurate time. They would come up with tables of numbers. Let's say they were using the Meridian Circle Telescope to come up with star positions for something like they used to do stellar parallax measurements, which gets you distances to stars and things like that. You're writing all those things down by hand, and that's just the number that you get, the time that you get from observing, and then the circle part of the meridian circle gives you another number. You put those two numbers down, those are your observation. And then there's a long series of calculations you have to go through to turn that into a position on the sky. And that was the sort of thing that, of course, in those days was carried out completely manually. There were no electronic computers or anything to do that kind of work.
And what kind of staff for Washburn?
So in the early days, Washburn had a director, and the director was a professional astronomer. And Edward Holden, who we saw at that beautiful Meridian Circle telescope, was hiring assistants from his courses. He was hiring students, men and women, to play a variety of roles in the observatory. In this particular era, in the late 19th century, it was very atypical for women to be afforded time observing. It was believed that night work was not for women, and so most time on the telescope actually making those observations was reserved for men. But the student assistants, which included women, they were the ones who were performing those hand calculations on big, long spreadsheets, really taking the observational data that the observer, the astronomer, was making at the telescope and translating that into useful data.
I'm just wondering what kind of majors these students would have had.
Yes, so at the time there was nothing like an astronomy major at the university. Many of these students might be science majors, for instance, just a very generic major. Holden had a joke that I'm sorry, it was Joel Stebbins. He was the fourth director, and he had a joke that women were just as capable as men at astronomy, but probably much neater, and probably was very true. But one thing that was somewhat unusual at Washburn and with Edward Holden in particular is he did have some of his female assistants were actually afforded time observing. Alice Lamb, for instance, is one of the student assistants that we have quite a bit of record on, and she and her eventual spouse, Milton Updegraff, were student assistants under Holden, who, when Holden left for a different job at Lick Observatory in 1885, Alice and Milton basically kept the observatory running. So between the two of them, they were at the telescope making observations. They were publishing in the publications of Washburn Observatory. And Alice would go on to accompany Milton over to Argentina, actually, where his astronomy career continued. She really desired a career in astronomy, but that did not pan out for her in the era.
Do you have a sense of, you mentioned the Lick Observatory, and there were, of course, many others in the country by this time, we get into the late 19th century. Do you have a sense of to what extent they were competing and to what extent they were collaborating?
There was a lot of collaboration in the sense that the astronomers would always share results. In fact, Kelly mentioned the publications of the Washburn Observatory, which were published for many decades. The patterns of science were shifting in the early 20th century, and astronomers started publishing in journals. But the publications were printed up largely for, in part for sharing results, but in part to have something to trade to other observatories for their publications. And so there was a very active network of these sorts of things, of astronomers sharing data. And then they would specialize in areas that they were well equipped for. So the Washburn Observatory, for example, was an early specialist in coming up with these stellar parallax measurements that came from that meridian circle. And other observatories, Lick, for example, had different specialties in spectroscopy, for example. We could say the same thing about Yerkes Observatory. So they had different specialties, and the astronomers had different interests. The competition maybe was friendly, I'd have to say, yeah.
One thing that ultimately set Washburn Observatory apart from some of the other observatories of the era, we've talked about Harvard. Harvard really invested heavily in the early 20th century in photographic astronomy, and so they were using their telescopes to essentially take pictures of the sky the same way that Hubble telescope does today, and they were then looking at those pictures and making observations and measurements there. Washburn made a different choice, and I think Jim can speak a little bit to how that choice was made and what that ultimately led to.
In the earliest days, it was these position measurements that we were just talking about. And it did lead to certain applications that, for example, figuring out the orbits of these binary stars based on position measurements, which is very laborious work, by the way, because, again, all those observations are done eyeball at the eyepiece, and then data reduction done during the daytime. And it resulted in some cases, in insights into the nature of stars, into the masses of stars and things like that. Very early contributions to what we might now call, what we would probably call astrophysics, in terms of thinking about the actual physical nature of these things, what's the mass of a star. But that style of astronomy was changing very rapidly in the early 20th century, in part because of photography, because astronomers found that eventually they could make observations of star positions more accurately photographically than they could with an instrument like a meridian circle. So Washburn, if it had followed the patterns that it had in the late 19th and very early 20th century, Washburn Observatory would have been pretty much obsolete by the 20s, when modern astrophysics started coming in. But the fourth director of Washburn Observatory came here, actually had been a student at the Washburn Observatory for a year earlier in his career, came here as the fourth director and was experimenting with the electronic measurement of light and measuring the quantitative measurement of light, which we call photometry, was something that could be pursued either photographically or electronically, and most astronomers were much more comfortable with photographic methods. But the electronic methods could give you much better results, much more accurate results. But very few astronomers were willing to mess around with the electronics of the 1920s. Think of a radio from the 1920s. In fact, Stebbins would occasionally say, well, think about a radio attached to the end of the telescope. This enabled them to do science that nobody else was doing because very few other astronomers, I won't say none, but very few other astronomers were willing to learn the electronics. And Stebbins was, and he also partnered up with physicists to help him develop these instruments. And they were able to come up with science that was very important in the early days of astrophysics in terms of understanding not only the natures of stars, for example, but even the structure of the galaxy.
But if we're looking at photoelectric photometry, is that Stebbins that we're seeing still eyeballing through the telescope?
Well, no. That's one of the interesting things. I like that. It looks as if Stebbins is looking through the telescope. He's actually looking at a microscopic meter. He doesn't see the light from the telescope. It goes into that detector tube. And what Stebbins sees through that little microscope is a microscopic needle that's creeping across a screen that's measuring the microscopic current that comes off of that tube. So he's not looking through the telescope anymore. It's not eyeball at the eyepiece. It is eyeball at the electrometer at that point, but not at the eyepiece.
Now, you're talking a lot about stars, distant objects. Were there interest at all in looking at planets, or are they just too close to be interesting at this point?
Certainly, many astronomers looked at planets when they were, say, when Mars was at opposition and relatively close. But actually, planetary astronomy in the early 20th century was kind of sort of a poor stepchild. There wasn't very much science that you could do observing planets.
You get a closer and closer image, but not really learn that much about anything?
The atmosphere kind of limits you on how much detail you can see, even with big telescopes.
The Earth's atmosphere.
The Earth's atmosphere, right. And so it was, people did planetary astronomy, but there wasn't a great deal to be done about that beyond, say, counting moons and measuring the phenomena that you could see. There were some very minor avenues that Stebbins pursued that do amount to planetary observation. But no, for the most part, it was about studying problems in stellar astronomy and the nature of stars. In that period, it was still a mystery how stars produce their energy. How does that keep up for so long, and how long will it keep up? What are the sources of it? So coming to terms with the nature of stars was one thing that Stebbins could derive from the photoelectric astronomy.
So they gave up looking for Vulcan pretty early on, I guess. Kind of almost legendary search for this planet that may or may not have existed in our solar system.
So there is a connection there at Washburn Observatory very early, but our first director who wanted to do that, James Watson, died too soon to carry out his plans for that, and nobody else followed him up on that.
And he did build an observatory in the hill for expressly that purpose.
What are the astronomers at Washburn then starting to discover about the nature of star power?
Well, so for example, the trace there, that light curve that shows the way the light changes in what's called an eclipsing variable star. There's a plunge in the brightness, which is called the primary eclipse, and then a little while later there's a smaller plunge in brightness that's called the secondary eclipse. Those curves, Stebbins is measuring those with his photoelectric photometer, looking through that little eyepiece and writing down those numbers. But in the case of the eclipsing binary star.
And these are stars that are in an orbital movement where one is passing over the other. So that's the eclipsing part of that.
Exactly right. Yeah. So when the dimmer one passes in front of the brighter one, you get a big dip. So this was known to be that there were stars that would do this. But the accurate measurements that Stebbins could make allowed him to derive things like the relative sizes of the stars. And that diagram that you see there is one that he published showing the relative sizes of these two stars. And if from studying the orbit of the stars you get the masses, then the masses and the sizes give you the densities of stars. So this is the beginning of understanding the physical characteristics of stars that would lead to not too many years later, by the mid-1930s, the conditions that existed within stars were enough that astronomers could come up with and physicists could come up with their theories about thermonuclear reactions going on in stars, and that being the energy source of stars. But you've got to know all those basics, mass and density and things like that, before you can begin coming up with your theories about where the energy comes from.
Are they looking specifically at galaxies at this point?
So galaxies were barely even a concept in the early 20th century. The word galaxy literally meant the group of stars that we live in. And what we now think of as other galaxies were little smudges, little swirly smudges out there in the sky, and people didn't really know if those were things as big as our galaxy or if they were some other type of object. But understanding the star system that we live in, they would have called it the stellar system, which we would now call our galaxy, had a very important development here at Wisconsin, again from Stebbins' photoelectric photometry, because he was able to determine distances to objects that showed how big the galaxy was and show that the galaxy actually contains a lot of matter that isn't stars. And he could talk about how that affects the measurements and how much matter that is. So all of that stuff from that photoelectric photometer on the Washburn telescope.
He's quoted as saying that we shrunk the universe because by being able to take those measurements, there had been lots of conjecture about the size of the galaxy, and Stebbins and scientists at the time were able to establish the galaxy is actually smaller than we thought it was.
Did that impression hold? Because it seems to me it keeps getting bigger.
No, actually, the number that Stebbins estimated for the size of the galaxy is very close to the number you'll find in modern intro astronomy books. About 100,000 light years in diameter.
Of the galaxy.
Give or take. Yeah, about 100,000 light years in diameter, the Milky Way
Start
galaxy.
seeing these other galaxies. And by the way, can we see any galaxies with the naked eye and just not recognize them as such?
Sure.
The Andromeda galaxy is one of the easiest. To the naked eye, it looks like a smudge in a dark sky, but that is a galaxy that is visible to the naked eye and our closest neighbor, galaxy neighbor.
And now we have good distances for that kind of thing, but in those days, they didn't really have much idea of the distance of these things or their size. You got to know one or the other to figure that out. And so it was very much up in the air, just what was the nature of these other things out there that we now call galaxies. They called them nebulas. Spiral nebulas is what was the common term.
Did they have a sense at all at how galaxies are formed? Are they seeing formation of galaxies at this point?
No, that's a much later sort of thing. The ideas of galaxy, theories about galaxy formation, and then galaxy evolution, and these days a very important thing is galaxy interaction.
Sure.
Yeah, those would come later, well after the Stebbins era.
A lot of the science that was the groundwork for that science was being laid here and elsewhere, but really, as Jim mentioned, the pivot to the photoelectric effect and really looking at electric astronomy really helped move the astronomical field in that direction. But importantly, it helped establish Wisconsin as a place where innovative technologies and instrumentation were being developed, which then also led into additional pioneering science.
Have they seen any collisions of galaxies at this point? And if so, what was going on?
No, in that period, no one was, as far as I know, was thinking about colliding galaxies. Certainly, there are many cases now. There's lots of that. That's a very important process to understand. And it would appear that most galaxies evolve in part by absorbing other galaxies, colliding with them, and eventually merging together. So that's pretty well understood and constantly being studied by modern astronomers. But that's a much later thing than what we're talking about there in those days. But as Kelly said, it did that kind of work, and the development of that technology here did set up Wisconsin astronomers to carry on this kind of research, much of which is done with space-based research. The specialty here in electronic astronomy, we could call it, set up Wisconsin astronomers for the early days of the space age and using early space technology and satellites to do observations in space, the way a lot of those great pictures that you see of colliding galaxies come from the Hubble telescope. And Wisconsin astronomers were developing the predecessors to the Hubble, and even pieces of the Hubble have been done here.
In that context, what are electronic astronomical detectors detecting?
They're sensitive to light both in the optical, but also in the ultraviolet and also in the infrared. The thing about the ultraviolet, for example, is that we don't get much of that, hardly any of it on the surface of the Earth, just enough to be a nuisance for those of us with light complexions. But,
yeah, sure.
The ultraviolet light that would be useful for astronomers doesn't make it through the Earth's atmosphere. You've got to be above the Earth's atmosphere. So those kind of electronic detectors make it possible to detect light that we couldn't observe here from Earth, but we do have to send those electronic detectors out into space. And so when the early days of the space age came along, which basically made it possible, then you got a rocket big enough to put a satellite in orbit, you can maybe use that to do some astronomy. And Wisconsin astronomers were well set up to build instruments that could be launched into space and used for astronomical observations. So we were some of the pioneers of space astronomy here at the University of Wisconsin.
And that gets back then to Hubble and some of its contemporaries in terms of extraterrestrial astronomy. Is that what you would call it?
Yeah, we usually just say space astronomy. Yeah.
All right.
Yeah. Right. So Sputnik was launched in 1957, and NASA was formed, not coincidentally, in 1958.
Yeah, in a kind of a rush.
Yeah, in kind of a rush, yeah. NASA began funding astronomers to figure out what they could possibly do with a satellite. Again, the Wisconsin astronomers were very well set to explore that, because operating an electronic detector in orbit is way easier than operating a film camera in orbit for any number of reasons. So that led to a pretty long line of space instruments coming from Wisconsin, ultimately in building, of course, a photometer for the Hubble Space Telescope. And in fact, there's the instrument being built for the Hubble telescope. There's the Hubble telescope, but then also the instrument that was our photometric package there. The astronomer there on the left is Robert Bless, who developed that instrument, and his project manager, Evan Richards. They and their teams produced that instrument, which was launched with the Hubble. So the reason there's a Wisconsin photometer on the Hubble telescope is because Joel Stebbins came here in the 1920s.
That's quite a long reach for Joel Stebbins. Hubble, there was sort of a little bit of a joke going around about Hubble at first, that it needed bifocals. They needed to kind of make some adjustments once it was already out there. How did that relate, if at all, to Washburn?
Right. The problem with the Hubble telescope when it was first launched was the mirror had not been correctly made. It had the main mirror had been incorrectly made, so that it produced out-of-focus images. And so, yeah, that's the joke about putting glasses on the telescope, is to correct those out-of-focus images.
Thankfully not a Wisconsin error.
No, certainly not. But we did suffer because of that, because our instrument then had to be used with those very imperfect images. But it badly affected all of the instruments on the Hubble. The saving thing for NASA was that those instruments could be replaced. And so other generations of instruments were installed by subsequent visits of space shuttle astronauts. And so the Hubble operates up to full spec today. But that was an awkward beginning, but not our mistake.
A lot of details to keep up with there.
Yeah.
Hubble is in orbit.
Orbit around the Earth, that's right.
And that's how the space station could kind of just intercept it?
The space shuttle.
Space shuttle,
yeah, that's right. They would launch the space shuttle in such a way that it was in the same orbit as the Hubble, and then it could approach, and the astronauts could work on the telescope up there.
any risk once you get something like Hubble up there that the technology is going to outpace it?
That's why it was designed to have replaceable instruments. Some of those instruments on the Hubble today are third generation instruments. And yeah, they've taken advantage of advances in technology for better instrumentation all the way along.
There's been a lot of innovation since the 90s when Hubble was first conceived.
Yeah.
This gets into that question that astronomers inevitably get, but here it is. I mean, how is something like Hubble, a big project, expensive project, long ongoing project, what's its actual mission in terms of practical things? Or is it all just out of scientific curiosity?
Well, certainly the scientific curiosity is what drives us. That's the finding the answers to these questions that we want to understand. Why are there stars, and how do they shine, and where are we, and what's our relationship to the rest of the universe? Those are back there, but finding answers to those are far from the only benefits that we get from that kind of work.
I think that's true of a lot of basic science. It's driven by curiosity, just a human desire to know more about the world, or in astronomy, the universe around us. But we don't always know at the time that we embark on that science what the technology or what the findings or the innovations might lead to. I'm really inspired by astronomy because I think, not as an astronomer, I am not an astronomer, but that it really just taps into this essence of humanity, right? This deep desire that we all possess to understand, but that also helps us move forward as a species.
That said, many of the things that astronomers have discovered about the universe do have direct practical implications on the Earth. Notably, things like fusion energy, the whole understanding of that sort of thermonuclear chemistry that goes on comes out of investigations into the energy sources of stars, to then understand how that can be applied here on the Earth for everything from hydrogen bombs to someday electrical energy from such things. The drive to understand the energy processes of the stars is behind the investigations into that sort of physics. So there are a number of those sorts of things. You can go back to things like we mentioned earlier, the timekeeping or celestial navigation. In the early days, those were strong motivations for astronomy because nations needed celestial navigation. They needed this for commerce. And navies always needed this sort of thing, and you needed some astronomers who could help your ships navigate long before there were GPS systems. So you have lists of practical applications and sometimes practical outcomes from these sorts of things, but none of those are really why we're doing it. You never know where the benefits are going to emerge, and so you have to kind of keep on working on the basic problems and asking the basic questions, and you can hope that they lead to some practical things, and they often do.
A good, honest answer. That's right. I mean, the priority is just because we want to know.
I think that's right.
And what may come out of that could be a blessing. What do we learn about fusion then in these explorations of the universe? So fusion being sort of the holy grail, isn't it, of energy production here on Earth?
Sure. Fusion happens in a lot of different ways in the astronomical context in terms of the evolution of stars. The evolution of stars is really a matter of the evolving conditions in stars that produce different phases of fusion, first of hydrogen into helium, and then helium into heavier elements, and so on. And we see this happening out in the universe around us. Those sorts of things are probably not first in the mind of the engineers who are designing fusion reactors. That sort of thing is pretty well understood in the laboratory by now, and they have very specific goals. So I don't think there's much of an astronomical connection anymore, except that that was the motivation for understanding that sort of physics in the very beginning. So the fusion is a huge laboratory and engineering problem now, and we do that on the UW campus too, fusion research. But again, it has little to do with the astronomers these days.
With a telescope like Hubble out there, what, a couple hundred miles, orbiting well past the Earth's atmosphere?
Yeah,
and
or just past.
and getting a good clear look at things that we could not see from Earth. What is the role of terrestrial-based observatories like Washburn?
Well, so Washburn these days is a pretty small observatory. So Wisconsin astronomers have much bigger telescopes to draw on now.
And as we alluded to earlier, the conditions here in Madison are no longer conducive to productive observation. Certainly we can observe.
Atmospheric interference.
Yeah,
Yes.
so you look for arid mountaintops and things like that. That's where you want your telescopes
You want
these
it
days.
high and dry and dark.
But the Hubble is, you put it correctly to say that its advantage is that it's above the Earth's atmosphere. It's not an especially large telescope. It has a mirror that's 2.5 meters in diameter, which is way bigger than the Washburn telescope. But Wisconsin has a ground-based telescope out in Arizona that's 3.5 meters in diameter. The Hubble's advantage is not in its size, but in its positioning above the Earth's atmosphere. So the Earth-based telescopes have their role in being a lot bigger, in collecting a lot more light and being able to image dimmer, more distant objects and phenomena than a telescope like the Hubble can. Also, there's an awful lot of, there have never been enough astronomers to look at everything in the sky. And so the Hubble keeps busy observing one thing after another, but the research programs that astronomers can come up with way exceed the available observing time, even with something like the Hubble. And so ground-based observatories all over the world are pursuing various sorts of research programs that can't be carried out with the time that's available just on that one, on the Hubble telescope.
I guess they have the advantage of being a little bit more accessible than Hubble.
Well, yeah, there's that too, yeah.
Although these days astronomy isn't done eyeball at the eyepiece like it was at Washburn, so data comes in, it's electronic, and so researchers can just access these troves of data sets now to essentially mine any question they want to ask. The competition comes in actually getting time on these ground-based instruments to point the thing at the object you are interested in looking at.
But your comment about accessibility, though, is well illustrated here. There are some of our people working on an instrument before it goes to a ground-based telescope. In that case, that's not a space instrument. In that case, you can get it as close to right in your laboratory, but then you do still get to work on it once it's on the telescope out there, and you can even iterate. We can make better ones, or we can improve that one. So access is, especially in instrument development, is an important advantage as well. The space stuff, once you get it up there, it's pretty much there. You don't get it back usually.
But are you saying then that a telescope such as the one in Chile, or even the UW one in Arizona, can actually see farther than Hubble because they're so much bigger?
Well, yeah, the way to put it would be the bigger the telescope, the dimmer the light source it can pick up. Yeah, and that could be dim owing to distance, could be dim owing to being small, if it's nearby. So greater light gathering power is what we usually call it. With the bigger telescope has the greater light gathering power. The Hubble, again, has the advantage of being above the Earth's atmosphere, which degrades the images that ground-based telescopes can create. So it gets a nice clear view of the sky. Another advantage of being in space, the Webb telescope, that we talk about a lot these days.
Famous now, yeah, see a lot of images from the Webb.
But its specialty is detecting light that doesn't penetrate the Earth's atmosphere at all, in that case in the infrared. So early Wisconsin space astronomers were exploring the ultraviolet. And so getting your instrument in space, whether it's infrared or ultraviolet, is another really important reason for developing those kinds of instruments.
And this telescope here is the Southern African Large Telescope, and UW-Madison is the largest of a consortium of partners that basically help keep this telescope operational in South Africa. It's in the desert, the Karoo. This is a 10-meter telescope, which means it just has a massive, massive set of hexagonal mirrors that act as a giant light bucket, right? So it's collecting as much light as possible, and 10 meters is a really large set of mirrors. And it also has an instrument on it in the near infrared, so it can't get infrared, but UW scientists actually worked with South African scientists, but here developed that new instrument that went to the telescope in 2022.
These wonderful pictures that we're seeing online now everywhere, these fantastic pictures that are inconceivable from somebody naked eye standing in a clear desert climate, cannot imagine these clouds and the colors. And I was going to say galaxies, but galaxies of stars. Are those actual photographs? What is the technology? What are we actually seeing? Is it a computer simulation?
Well, certainly, generally speaking, we're seeing images created by telescopes of different sorts. But sometimes, in the case of, say, an image from the Webb telescope, those observations were made in the in the infrared, middle infrared or far infrared. And so when they put in colors and things like that, they're basically they're assigning codes of certain colors to correspond to certain wavelengths that we can't perceive at all. So those colors are sometimes called scientific colors or false colors, but so those sorts of things are not an image in the sense of what you would see in the sky if you could be out there at the Webb telescope or something like that. But the ones that are created in the visual from the ground sometimes are created the same way, or sometimes they're created in such a way that maybe if you had eyes that were 10 meters in diameter, that maybe it would look like this. That's all kind of silly in a way. What the real power of these things is that astronomers can understand the physical phenomena. So when you see, for example, a lot of pink in an image like that, and this is an image from the Rubin telescope, which was very recently brought online. That pink there is telling you where hydrogen is glowing. And so an astronomer can look at an image like this, and from the nature of the image and the distribution of wavelengths at one point or another, you might think of it as distribution of colors, but it's way more specific than that. They can understand the composition and the conditions, and even things like the motions of the various parts of an object like this. That's a vast star-forming region.
Yeah, the pink one is the Lagoon Nebula, and the bluish pink at the top there is the Trifid Nebula.
The Trifid Nebula. That sounds like a science fiction movie from the 60s.
These are complex. Maybe that's where it came from. These are complexes of dust and gas there, where stars are forming. And star formation is something that's very interesting for astronomers to understand, because ultimately planets come from that too, and ultimately we come from planets.
As Carl Sagan once famously said, we are all stardust.
Right. So understanding that stardust is understanding ourselves there. So
we're all recycled, that's what it comes down to. It's a little depressing, but exciting too.
Original sustainability.
Yeah, right.
Speaking of images, this is actually not just one image. This is 678 images stacked together that were taken over the course of 7 hours to yield a picture of these two.
So a composite.
Yes.
And it's a very wide field of view. A typical telescope, the Rubin is specifically designed to do this, to have a very wide field of view. And normally, to have that kind of field of view, a typical telescope would have to make many little pieces and stitch them all together, and that would take days or worse.
And lots of computing power to make happen.
But here the Rubin can do it in basically minutes.
Are we talking AI here?
Probably-
Not in the production of the image.
Yeah, probably just a lot of high power computer science that.
Data analysis.
Yeah, well, there's a huge amount of computing going into making those images, but I don't think you would call it AI. Now, the AI could come in when astronomers have enough data to look at, say, different examples of star-forming regions, and then ask AI to try and generalize about what are the essential conditions that go into these sorts of things, something like that. It might come into the thinking about the problem down the road, but no, not the production of the image per se.
Or asking AI to analyze patterns that might be missed by a human observer.
Well, as long as we're talking about star formation, can you give us a timeline for forming, I don't know, a yellow dwarf or red dwarf or whatever it might be?
Well, it sort of depends on where you start. So out there in that star-forming region, there are knots of molecules and gases that are called molecular clouds. And those clouds, under circumstances that there seem to be a number of mechanisms that can trigger this, the cloud can begin to collapse on itself gravitationally. So if you start the stopwatch running then understanding how fast that can happen is something that astronomers are very interested in, and studying large clouds like this, because you can see finished stars in there, and you can see these cold molecular clouds in there. And it varies probably on the size of the cloud and how big the star is, but it happens over a period of hundreds of thousands to a million years, which is fairly fast.
I was going to say, to make a star a million years?
Yeah.
Pretty good.
Right. It's but then where do you stop the stopwatch? Because they're never quite done. Do you stop it when it's got a planetary system and it enters what the astronomers call the main sequence? That's probably where you could agree to stop it. But we actually understand those sorts of things relatively well now. The problems are far from solved, but compared to 100 years ago, we're able to talk about these things in terms that the astronomers of Stebbins' era had no clue about. In fact, even the very idea of star formation, star and planet formation 100 years ago, this idea of the collapse of clouds, which had been tossed around, was actually on the outs. People didn't think that was a very good theory, and there were some competitors. So it's in the past 100 years, we've come a tremendous distance in our understanding of things like star and planet formation, which is far to say, not to say anything like we're close to being done, but we have such powerful insights into that now that it makes everybody want to know more and understand better where, say, planetary systems come from.
And we're seeing more and more. It seems to me we're finding more even so-called Goldilocks planets now.
Oh yeah. Well, I mean, what's it been? 25 years? How long have we had exoplanets? It's finding any star systems beyond the sun is a relatively recent thing.
Is that done through transits where you can see them crossing the face of a star, or is there more analysis to it?
Well, certainly that's one way. Yeah, that's been one of the more productive methods of finding exoplanets. There are other techniques as well that are less direct than actually seeing that eclipse. But the era of direct imaging of planets around stars is the Webb has been able to do this in a couple of cases. We may be on the verge of that, of seeing these things, at least a few of them directly around stars. But very often when you mention a Goldilocks planet, you're looking for this is a planet that's at the right distance from its star, that it can have liquid water on it is usually what the criterion is. And there will inevitably be more of those just because the total number of known exoplanets, whether they're Goldilocks planets or not, is going up. So yeah, there are more and more of those, but the planet detecting programs are going great guns, and that's a very exciting thing these days for astronomers too.
One of the things that has long set Washburn apart from so many other observatories is the role it has in public engagement. And can you give us kind of a history of that and what that public engagement has produced, other than just people fascinated by looking at stars?
So when Edward Holden got to the observatory as the second director, he decided that he was going to maintain a public observatory. So the observatory was built with an infusion of money from Governor Washburn, but also Washburn helped Bascom ensure that the telescope was supported by the state legislature. So at the time, it was at the amount of $3,000 per year. The state supported basically the science that happened at the observatory. Laugh because I think it's the first example of public-private partnership at uw-madison or the University of Wisconsin. But Holden really valued the idea of a public observatory. And so long as the observatory wasn't in use for specifically for a scientific mission, it was open to the public on, I think, the first and third Wednesdays.
From the very beginning.
From the very beginning.
Wednesdays was the day from the beginning.
Yes, and it continues.
From 1881.
Yeah, to this day. So from 1881 until today, Washburn Observatory is a place that people can come and look through the refractor.
And then, of course, there have always been special occasions. When Halley's Comet came by in 1910 and people were clamoring to see it. And this happens today, too, when there's some...
Well, it came back, in 1985, right?
It did, although that was not so good. As we couldn't really see it as well as they could in 1910. So I don't think anybody tried to see the Halley's Comet with the Washburn telescope. Somebody might have, but
atmospheric difference?
Mostly orbital difference. I mean, it was just way
different position.
Favored southern observers way over northern observers in 1986. But the point is that when there are these things of enormous interest, we still open up the observatory extra nights, and they had to open up lots of extra nights during 1910 when Halley's Comet was in the press and in the sky. And this still happens from time to time. But yeah, the regular nights are the first and third Wednesday nights, weather permitting, of course. And then in recent years, the astronomy department has been doing every Wednesday night, June, July, and August. Weather permitting. So this is a long tradition here, and you asked about, in addition to just letting people look through the sky, it's been great for the students and the astronomers, especially our graduate students who run that program now, to have an aspect of teaching astronomy, and in that way to meet the public and answer their questions and help them go back to eyeball at the eyepiece astronomy and enjoy the sorts of sights there are to see in the sky.
So if I were to stop by Washburn on some Wednesday evening, what would I most likely get to see?
Well, that'll vary with the time of year and what sort of things are available. If there are bright planets, then those are very popular. Everybody wants to see Saturn or Jupiter, or if the moon is up. And the whole evening can go by, and you never look at anything but whatever planets and the moon are
planets.
up there.
Yeah.
Well,
Some of Jupiter's moons, and that's always fun to count how many you can see at any given time.
So those would be typical, but then once you get past planets, or if you don't have any planets that night, which certainly happens, the telescope is very well adapted to things like binary stars, star clusters, and some bright galaxies. The sky here in the city is too bright now for galaxies to be too much, or nebulas like the image that we had of the Lagoon Nebula or the Trifid Nebula. Those are low in the south for us, but we can pick those up. To the eye, they don't look anything like those images. You don't see any colors in them or anything along that line. But we can introduce the people to a wide range of astronomical objects with that fine old telescope.
There's a wonderful juxtaposition of Washburn Observatory that I don't think you would find anywhere else in the country, maybe not in the world, which says so much about astronomy, or at least people looking at the sky, looking at the stars and the planets over a long period of time. And Washburn is actually on a hillside that had 3 effigy mounds on it, which clearly had some sky significance to the builders. And here it's right next to Washburn. What kind of a sense do you get when you go up there and see that effigy mound right next to the observatory?
I think it's a really powerful reminder that as long as we've been on this earth, we've been really curious about the night sky and the connection between earth and water and the heavens. I think it's a really important thing for us to remember, that though we've talked about sort of the more recent modern innovations in technology and in science, that as long as we've been humans, we've been fascinated by the stars.
It is, as you say, it's a wonderful juxtaposition to know that people 1,000 years ago, or whatever the date of the mounds is, were up there on that hill, and it was a special enough place to them to build those mounds, and they must have been aware. All human cultures have been fascinated by the sky, and so it's been a special place there for that distant culture as well as our own
Human curiosity.
Modern.
Human curiosity carrying over the millennia.
Yeah.
And you can see it right there on the hill and Washburn Observatory. Jim Lattis and Kelly Terrell, it's been a real pleasure looking skyward with you.
Thank you so much, Norman.
Thank you, Norman.
They're the co-authors of the book, Chasing the Stars. I'm Norman Gilliland, and I hope you can join me next time around for University Place Presents.